Hello and welcome back to Learning Image Analysis. I'm Lawrence Small. This lesson we'll be discussing cleaning a messy segmentation. So the image that we have today is one of some two-layered nanoparticles. So these nanoparticles have a core in the center and a shell around the outside. And what we want to do is measure particle size. We also want to measure particle roundness. And then to get at the internal structure of the particles, we want to measure the percent of the particles that's core as opposed to shell, and also the thickness of the shell. So our learning objectives: first, planning desired selections. So what features do we want to have selected? What type of segmentation do we want to have to produce the measurements that we listed on the previous slide? We also want to talk about comparing types of noise reduction. What type of pre-processing filters can we use to make the segmentation more clean? So if we look at these nanoparticles, we can see that the shells have a lot of speckling inside them, and the cores do as well. A lot of variation here in the image. So what types of pre-processing can we use to minimize that? And then the main part that we'll talk about today is cleaning the segmentation using morphological image processing. So of course we can't get things perfectly clean with the pre-processing. So we're going to have to do some cleanup once the segmentation has been produced in order to remove noise to get the segmentation looking nice. So switching over to MIPAR now. Now looking at this image, the first thing that we want to do is just select the whole particles and have them separated. That way we can get a size measurement for each particle, and we can get the shape information for each particle as well. So as in the previous image in the previous lesson, the particles are all pretty consistently darker than the background. So if we start just naively with a basic threshold and say put it here, we can see that actually this gets pretty good, pretty close. We have a little bit of selection that needs to be made here in the middle, and a little bit of cleanup to be made around the outside. So this actually isn't bad, but we can do better. Let's try running a smoothing filter on our image to make it a little more clean. So we have really two options when dealing with speckled types of noise. The first is the median filter. So what this does is it looks at a window around a pixel and assigns to that pixel the median value of the window. So that has a tendency to ignore outliers, to ignore large bits of noise. So if we set a window size of 5 here, you can see that a lot of the speckling goes away. And it's pretty good at preserving the locations of edges. See that edge stays in about the same position. We can see the bright highlights going away because those are outliers that get removed with the median. What it tends to not do very well is preserve boundaries between particles. So all this is going to be smoothed out like this. Now we can fix this in post with our separate features, but let's see if there's something we can do to make that not as necessary. So let me save this for later and pull back our original. And we'll try our non-local means filter. What the non-local means filter does is use information from elsewhere in the image as a way to interpret what's likely going on inside each window. So if we set a window size here of 2, it's taking 2 pixel windows and then looking around in the image for other windows that are similar, and it uses those to produce an average, smooth, non-local mean for each window. So it's also good at removing high frequency noise, removing speckling. But what it'll do is, if the variation is strong enough, like here, then it won't get removed. So the filter will say, well, this is something pretty intense. This is probably something different than the rest of the shell over here. So I'm not going to adjust it. And it helps save some of these boundaries that were removed by the median filter. So if we tone down the strength a little bit, say 1.5, and it's not perfectly smooth, but it's pretty good there. And something you can do with the non-local means is actually repeat it to get further smoothing on the fine parts, the small variation, while continuing to preserve the intense variation. So original, first pass, second pass, and we save this really nice boundary here. So if we have this now as our pre-processed image, let's see what our basic threshold looks like. See? Much cleaner than the unprocessed. Okay. So let me remove these. They're unnecessary anymore. And we have our basic threshold. So let's now clean up this nanoparticle selection. We'll start by filling in these tiny holes. So if we measure some of the holes here, they tend to be around 50 pixels, 30, something like that, compared to these spaces which you don't want to fill in, which can be on the order of several hundred. So if we set our cutoff here at, say, 150, remove little holes like that, and then we'll use our separate features function. Separation, let's see what one does. Okay, and very good. So now we have, if we label our things randomly, we have individual nanoparticles. Now for getting size and shape information, of course, we don't want to measure incomplete particles on the edges. So we'll clean up, remove edge features, just like that. Right? Whole nanoparticles. So now let's move to finding the cores inside. So if we take our pre-processed image here, saved away and call it back, and try to use our basic threshold to find the nanoparticles. And what we see here is that it's a little bit fragile on where this value should be. So if we focus specifically on these two nanoparticles, we'll see that in order to get this whole core selected, we end up selecting shell on this darker nanoparticle. So there's maybe a value right there, which looks pretty good, but that's a very very fragile number. It's not likely to be consistent image to image as you get some of this variation. So what that tells you is our pre-processing here that we did was a little bit too strong. Okay, if we had some of the variation still in here, that variation might have cut this part away, and we wouldn't have such an all or nothing switch here. That would give us a little bit more wiggle room in the values to produce a nice segmentation. So rather than starting with this really strongly preprocessed image, to find the cores, we'll do a little bit less. So say we have our median filter with a window size of 3, which will help out some, but we'll need to do some now post-processing of the segmentation to make up for the fact that we haven't been as heavy-handed in our pre-processing. So say we set our value right about here. Okay. 130, yeah, 130 looks like a good number. Most of these look pretty clean. Perhaps a little bit less to cut this off. Yeah, that looks good. And now we've got some cleaning to do. And here also we have a decision to make. There's a lot of this roughness, this globularness around the outside of these cores. And we have to decide, is this real or is it not? Is this real variation in the size of the cores? Like, are they actually in real life jagged like this? Or is this just an artifact of the imaging, the intensity variation that we have here? So let's try it both ways. Let's first say that we expect the cores to really be smooth in real life. Well, that saves us a lot of headache, because what we can do, rather than worrying about filling all these in, is use or replace with convex hull. So we simply replace the whole core with a convex hull around it. Okay, and so small pieces like this that are outside won't be found or won't be connected to the main core. And we can then remove features that aren't part of the convex hull. So if we reject features based on area, the cores themselves are several thousand pixels. The small extraneous features are under 100. So if we set our value here at, say, 500, okay, and we remove all the extraneous stuff, and these will be our cores. Now, the one thing that we have to do is note that we only have whole nanoparticles like this, not the ones touching the edge. So if we want to, of course, only have cores that are associated with these nanoparticles. So we'll take them and I'll make them a companion image, and then use this and intersect it with our cores here. And we'll only grab cores that intersect with the whole nanoparticles we found before. And so, cores. If I change the color here. And so now we have whole nanoparticles and our cores. So now let's go back and reverse our decision to use replace with convex hull. Say we really want the true rough edges of these cores. If I remove all this, now we're going to have to do some morphological processing to properly get the cores selected, to get the segmentation cleaned up. So we'll start with our classic erosion and dilation. Okay. And so I'm going to try dilating first. So we want to join pieces like this together, which look like they're part of the cores. And I'm not quite concerned about this larger piece getting joined because it's farther away than this piece is here. So we're going to start with an open. Start with a closing operation, which connects features together. So in order to close, first you dilate, say with a depth of 2. And now we're going to erode with a depth of 2. That's called a morphological close with a depth of 2. Okay. And now we have to, there are some borders that got made inadvertently. So we can do the reverse operation of morphological opening to remove these pieces as well. So erode, uniform, say 2, and open back up to 2. Right, and now I have a pretty good clean segmentation of these cores. And we'll again reject these features on the edge. This one's 33, this one's 18. These larger ones are a couple thousand. So say we set our cutoff at 500, update, and do the same thing as before, where we intersect these cores with the whole nanoparticles. Okay, and now these will be cores. Now, let's say that you didn't like the fact that our opening and closing tended to mess with the outsides a little bit. Okay, shifted this over some, and the border got a little bit messed up because of this interaction with the piece on the outside. Okay, and you didn't like how careful we had to be to choose this depth to not join these together while joining this together. So instead of these uniform dilations and erosions over the entire image, we do have in MIPAR a couple of additional smoothing operations that are available, specifically our smart dilation and smart erosion. So what these will do is take only pixels that meet a certain threshold, and that's a threshold of surrounding pixels that are selected. So say here we got this pixel with 1, 2, 3, 4, 5, 6 pixels around it that are selected. We set a threshold of 6, it'll get filled in. But that won't touch situations like this where there's a bunch of pixels with nothing between them. So we can set a smart threshold, say, of about 5, looks pretty good here, to fill in some of this without inadvertently connecting things that we don't want to have connected. And we could even go to 4 if we didn't care about these tight boundaries as much. Say if we did 4 with, say, 3 iterations like this. Okay. And that looks pretty good for doing some smoothing without inadvertently joining things that shouldn't be. And so now we can run the opposite, run a smart erosion. And if we set the same parameters of 2, threshold of 4, 2 iterations, and where does that leave our edges? Roughly the same spot. With our pre-cleaning now, we can do a little bit of morphological processing to make these a little bit better. See if we can get some joining here without inadvertent connections here. Again, there's always going to be a trade-off between selecting false positives and selecting false negatives. So, say we do a dilation of 2, about like that maybe, and an erosion of 2. Yep, where does that leave us? That looks pretty good. That also cleaned up this sort of gnarly looking core here. Looks a little bit better. And now we can reject features. So we should have about the same number that we had before. So we do 500. Accept. And fill all holes to fill that little piece in. And lastly, intersect with our whole nanoparticles to have the cores that we're interested in looking at. Now, you might take a little bit of issue with some of these segmentations to say that maybe this should have been selected as core when it wasn't. But that's sort of the trade-off you have to make. This didn't get selected, but that was for the purpose of not selecting things that might have not been core. So these spots on the shells, if we increase our basic threshold to grab that, of course all this gets found. So that's not a thing that we want to do. And we could have done a few more iterations perhaps here to be better at joining pieces that maybe should be included in the cores, like this piece here, which didn't end up being captured. But again, it's a trade-off that we had to prevent pieces like this from inadvertently getting added to the cores. It's worth mentioning, though, that these trade-offs are really small trade-offs. A little bit extra or a little bit missing. If we had stuck with our really heavily cleaned image, those trade-offs would have been much bigger. A whole piece selected or a whole piece missing. So the fact that we kept some of this original noise gives us a little bit more leeway when it comes to picking our values for post-processing. So here's what we'll have, and for our purposes we'll say this is where we want to have this trade-off be. you'll have to make that decision on your own for your individual applications. So I will now move on to selecting the shells. And the shells are pretty simple. We'll simply take our cores, stash them away, and then we have our whole nanoparticles, which I'll set as memory image 1 here, and call it back, and subtract the companion image from the current image. So that subtracts the cores from the whole nanoparticles to give us just the shells. All right. So let's proceed to our measurements. We can use measure features here to measure these whole nanoparticles. We'll get their, say, their equivalent diameter. So what that means is if you were to take this area here for this particle and squash it into a perfect circle, then the diameter of that circle would be the equivalent diameter. So we can grab its area, we can grab its caliper diameter, which is the longest line across an image. And if we want to measure how circular they are, we've got an eccentricity measurement. All right, let's view the results here. Okay, so pretty simple. Here's our largest feature. Here's our smallest feature. Okay, and we got eccentricity. There's the most circular one. And then equivalent diameter and caliper diameter. All right. So we can also add this. Say if we wanted the area, caliper diameter, the eccentricity, add the mean and standard deviation to the recipe here. Okay. And we can do the same thing for the cores. Get their area, their caliper diameter, and their eccentricity. Now let's do the area fraction of the cores relative to the whole nanoparticles. So what we see here is we'll want to measure the cores, the area of the cores, but relative to the area of the nanoparticles. And we have the nanoparticles stored in memory image 1 and in our companion image. So at our cores here, if we measure the area fraction relative to the companion image, okay, so if we have our cores, let me choose layers, relative to the companion image, that will give you an area fraction of 48.7%. So just under half of the area of these cores, of the nanoparticles is cores as opposed to shells. Okay. Lastly, let's measure the thickness of these shells. So this will be a per pixel measurement, the thickness of the feature at each pixel along its center skeleton line. So to do a per pixel measurement, we'll use our measure local tool. Okay, and thickness here, and see what our skeleton looks like. I'm not quite happy with these little pieces pointing out, so they're much better if we use a smooth skeleton. And we'll generate our thickness measurements. Okay, and we can see the thicker parts here colored in yellow, the thinner parts colored in a dark bluish purple, and a mean thickness right about 13 pixels And there we are. That was our lesson on cleaning a messy segmentation. Next lesson, we'll deal with noticing and fixing variation. So looking at an image and seeing that one part of the image does not look similar enough to the next part in order to use the same basic threshold across the image. So how do you notice that, and how do you fix it? I'll see you then.